Okay. Black holes are probably one of the most interesting and spectacular things in our universe. Everyone finds that probably the most interesting. Everyone knows something a little bit about it. And I will say that right now, we live in a very unique period of time regarding this particular phenomena, where we understand a lot more than humanity has ever understood about this thing. And it all started with the theories and ideas of, let me get my, where's my mouse? Theories and ideas of Albert Einstein and his general theory of relativity. The general theory of relativity really is based on a couple of things. One are his postulates of special relativity, which are, he started with two main postulates. One is the principle of relativity itself. Now the principle of relativity is not original to Albert Einstein. Actually, it's a very old idea. Originally started by Galileo. And what it is the physics of any operation, as long as that object, like right here, you cannot tell whether this person, the same activity, whether she is moving or not moving. And this was Galileo's idea, that all of physics are the same for all observers in relative motion. The next was the constancy of the speed of light in a vacuum. No matter what relative motion you were in, the speed of light would be the same. In addition to those principles of relativity, principles of postulates of relativity, it was the principle of equivalence also that came later. And what this basically explains is that given any small reference frame, and the reference frame is noted by the small box here, and we're going to be concerned with the one of gravity. If the person is in a very small reference frame, that if they were on Earth in a gravitational field, this person would not be able to tell the difference between being in space accelerating at the speed of g. These two things are not not only the same, these two reference frames are actually equivalent. So this postulates of relativity and the principle of equivalence between these two things are really the genesis of the idea of general relativity. I mean, if you're a chemist, these ideas would be, the atomic theory of matter. If you're a mathematician, these will be your undefined terms. The rest of it is just proof. All of that was used to describe curved space-time. And a lot of that was really misunderstood, but let's get this clear now. What is curved space-time? Well, let's imagine if space is flat. On a sheet of paper, if we draw two parallel lines, if space is flat, then parallel lines will never cross. If we had initially parallel lines and they did cross, then we would know that that space was curved. Do we have any evidence of this type of thing? In an idealized universe without gravity, there's no warpage of space, no warpage of time. Space-time has no curvature. Therefore, particles must travel along straight lines. Whenever a freely moving particle in our real gravity-endowed universe passes through a small reference frame, that particle must move along straight lines through that frame. Let's take this, and I'm a product of I went to school. Dictate in curved geometry a straight line path through that curved space. That's why I can take this ball and toss it like this. You see it follow a curved path. But Einstein says, nope, it's following a straight line path. You just happen to be looking at it in a funny way. When Einstein was working with his equations to make calculations on these things, he only found estimates of the amount of curvature, the geometry of that curvature. Let me tell you something. That's some wicked hard math, and we will not be going through any of that stuff. But there is a way, using those equations, to actually calculate the amount of curvature around a mass. Well, like I said, Einstein only got estimates for that. But this gentleman, Karl Schwarzschild, he was a German astrophysicist and mathematician. And he was a very patriotic fellow, and he was in the middle of the war, this is World War I, on the Russian front. And he he had gotten ill, and while he was in the hospital, essentially on his deathbed, it's about a year after Einstein publishes his theory on relativity, he calculates the exact solutions for that curvature around that mass, around masses. But in order to do that, just his approach was to treat the gravitational fields emanating from bodies with no volume. So essentially, he would take an object like a sun or the earth or whatever, and just use a point mass instead of using the entire volume of it. So in doing that, he discovered that the space-time curvature closes in on itself when it gets that size, and that the redshift becomes infinite. What do you mean by redshift infinite? Well, what it is that this gravitational redshift, whenever you have light or electromagnetic radiation emanating from a source, emanating from a gravitational source, it requires energy to emanate from that particular source. But because of that second postulate, we'll get to that in a minute. Here we have the electromagnetic spectrum all laid out. But as it emanates, the frequency of that light will change by the Doppler effect from that gravitational force. Therefore, if you had blue light at the surface of that gravitational force, it would then appear red as it approached some distance away from that source. But what he calculated was that this redshift had become infinite. These line waves had become infinite. Essentially, it would not be visible. Which was really kind of an interesting result. That by his particular approach, I don't know if it was happenstance or just sheer luck that he approached it that way, that he discovered that it would not emanate light if you would deal with this point mass. Let's take a look at the Earth, for example, on what it would take to have light not escape from the Earth. We take a ball, we knock it up in the air at a certain velocity, it goes up and it returns back to the Earth. We give it a little bit more velocity and it comes back down to the Earth, but it goes a little higher. But what we want to find out is we want to give it enough velocity where it goes up and then never returns back down to the Earth. We would call this the escape velocity. And on the Earth, that particular speed, that particular velocity is 11 kilometers per second, or 7 meters per second, or 25,000 miles per hour. Now let's see, to see what this means, let's look at the Earth again. Let's do a little bit of calculations, but we're going to use, I'm going to cheat a little bit. I'm going to use Newton's equations. So we have the mass of the Earth around 6,000 times 10 to the 24 kilograms. We have the size of the Earth at about 8,000 miles. So what we have here, and we're just going to start with this equation, and we're not going to do a lot of math tonight, so I'm going to go through this very quickly. This is the equation for the escape velocity. And you'll see it's 2g m over r. And m in this case would be larger than the mass of the Earth. What we want to do is find out how much we would have to shrink the Earth in order for that escape velocity, v squared, to equal the speed of light. So we are going to move the radius of the Earth out, divide, and we're going to, because we don't want any v squared, we're going to make it c squared. We want that escape velocity to be the speed of light. Once we set up the equation, it's just a matter of putting in our values. And then what we have is a size of the Earth to be, or have a radius of 8 times 10 to the minus 3 meters, or a radius of 8 millimeters. And what we would do is we would shrink this down, the size of the Earth, to a size of a diameter of 1.6 centimeters. Well, how small this, if Schwarzschild did it, he treated it as if it was all just a particular point mass, right in the center. But he noticed that that effect took place before it actually reached the point mass. That effect of not emanating light. And that distance from the point mass, the center of the point mass, to where that first, where it reaches not emanating light anymore, where space-time has been curved so much that light is not emanating, is called the Schwarzschild radius. That is the area where that escape velocity would equal 300 million meters per second. Now, at this point, he thought that was quite interesting. He sends the information off to Einstein. Einstein, Einstein did not know a lot about, he did not accept these results. As a matter of fact, a lot of scientists didn't accept this result. It was a mathematical curiosity, more like a parlor trick, because you could apply the same type of thing to anything that had mass. You could take this laser pointer, your pen, although you could do that sort of thing, and whether or not you can actually observe this type of density, to concentrate all of that mass, this type of density in nature was great debate for over several years. So basically, the idea as far as practical science was shelved. They didn't want to mess with it anymore because the densest thing known to man, and this is the early 1920s, late 1920s, during this time, the densest thing known at that time were white dwarfs, the matter of white dwarfs. And this was a particular study of Sir Arthur Eddington. He was an English astronomer, physicist, and mathematician who is the same gentleman who also verified the eclipse of predictions of, the warping of time of Einstein by leading the expedition to, was it South America or Africa?
South Africa.
South Africa. But he also investigated the interiors of the stars through theory, and in particular white dwarfs. He was a very respected man in his field. The white dwarf is they're about the size of the Earth, but they have the density of a little over 1.05 suns. A teaspoon of that matter could weigh us 5.5 metric tons on the Earth. Now, Eddington, he's the one who really investigated this and really verified these things. And he really looked at this when he did the calculations to find out the density of something this small, this dense, having this much mass. He looked at it and said, this is absurd. This is ridiculous. But it was later confirmed. But what exactly is the composition of a white dwarf? And we're looking at this from the late 1920s, 30s point of view. What would be the composition of this substance that can be so dense? Before we look into this, let's look at the atomic structure. If the distance from, if the nucleus of an atom were the size of a golf ball, the electron would be about 1.5 miles away. There's a lot of space there, a lot of space. As a matter of fact, when I first learned of a fact like this, and I may have been in high school when this idea came out, there's being so much space, and you would think, well, why could I not pass my hand through this table? I mean, if there's so much space in these atoms, why can't I do that? Well, as it turns out, there is a lot of electromagnetic forces there in the atom, between molecules, the bonding between the molecules of the particular table, and that the molecules are bonded stronger than the force of my hand. As a matter of fact, that's sort of like the definition of a solid surface, that you cannot separate those molecules by the simple pressure of my hand. So if we look at the atomic models, now this is the Bohr model. As a matter of this particular model, it's good for illustrating bonding between atoms, even light emission spectra. It's good for whenever I think of atoms, you really think of this model. But this model is very good, but it's is insufficient to explain this type of thing. What we need is a quantum mechanical model. And you see that the atoms really have a three-dimensional structure. They're not circular planetary, miniature planetary systems in structure. They actually have a three-dimensional structure to them. Electrons occupy specific orbits, and these areas or these lobes are really almost like probability
fields.
Sorry, what?
Probability fields.
Well, I was looking for something else, but we'll accept that for right now. A probability distribution. It's a distribution plot, a distribution graph for where you're likely to find these electrons. And but under such intense pressure from being in the core of the Earth, core of the sun, under such intense pressure, the three-dimensional structure of the atom is destroyed. The atoms cannot occupy. There is a particular principle called a Pauli exclusion principle. The electrons do not like being near each other. They resist each other, so they would rather destroy the atom itself rather than to be confined to each other. So what you end up with is almost a plasma of just protons and electrons in a sea of electrons swimming around. This is what you would call electron degenerate matter. Enter our friend Subrahmanya.
I just say Superman.
Subramanian Chandrasekhar. This gentleman came along the time where they had discovered that the matter of white dwarfs was the constituents of it was electron degenerate matter. At the age of 19, he had just graduated from undergrad, and he was on an 18-day voyage over to England. This is in 1930. He was able to establish the maximum mass of white dwarf stars to 1.4 solar masses. Now, this is pretty interesting. He used, and I'm gonna use another little demonstration here. He used, now this is a little magnet little demonstration here I have, and I built this myself. Now, essentially, this is going to be sort of my electron degenerate model. But the electrons are not the magnets. The electrons would be the magnetic fields between them. Now, I'm not in no way saying that an electronic field is the same thing as a magnetic field, but this is just for illustrative purposes. So what he determined is that as a white dwarf gains more mass, and here's the really interesting thing. We're all accustomed to adding sand in the sand pile, adding sand to the sand pile, and seeing the sand pile get bigger. But that only goes up to such a point. There is, when you get so much mass, the gravity of that sand pile will want to crush it. And that's the matter that white dwarfs are concerned with. The more matter you add to a white dwarf, it doesn't get larger. The gravity of that additional matter actually compresses that white dwarf. As that white dwarf gets compressed, the distance, now this requires a lot of strength here, and I'm going to simulate gravity compressing these things. I can feel resistance, okay? Those are the electrons resisting my powerful compression forces here in gravity. What Super Hunyan-Chandrasekhar did was, as that distance decreased, the activity of the electron would increase. It approached the speed of light. Quantum mechanics was new. He was aware of the general theory of relativity and the special theory of relativity, but he was the first one to give relativistic principles to this particular idea. And he knew that an electron being confined to that small a space could not travel into the speed of light. And it actually came out to being 1.4 solar masses, where he knew that it could not go beyond. There was an asymptotic dead end there. Now, whether he knew exactly what happened after that is, I'm not sure. But he knew that those white dwarfs could not go beyond 1.4 solar masses. So let's take a look and see at this a little closely and see where these white dwarfs come from. Because all this is related to black holes. White dwarfs, black holes, neutron stars, they're all dead remnants of what was once a star. And we all know stars are big balls of burning gas. So what better place to start with a gas that we're all familiar with? Gas around the earth. Gas around the earth, we're all familiar with it. We fly planes in it, we fly kites in it, we enjoy it, we like feeling it when it moves. We know that it's heated unevenly. We even depend on it for our very lives. But it has mass, and as a result of it having mass, it is under the influence of gravity. This gas that's around the earth, now, unlike the stars, there's a big rock in the way. But when it comes down, it puts the pressure on the surface of the earth. That surface pressure, and we don't even really know that. The only way that we're aware of the pressure that's being put down on the earth by this gravity is to cause some type of differential. And this can easily be done here. This was done in my kitchen because, believe it or not, there's some atmosphere in my kitchen. So what we created a pressure differential. The air in the bottle expands, goes down, we put the egg on top, and the outside air will come and push this egg right through the bottle. I only do this to say that these forces are real. These forces are all around us. These forces are not only here, but the forces that are going on, we constantly live with the same exact forces that are occurring in the stars. It's just to a higher degree. A lot of times, and I have to tell my kids about this all the time, a lot of times, this just isn't in books. It's around you all the time. Let's give a perspective of size here. You can see where the Earth is relative to the sun. There are about 1 million Earths that can fit inside the sun. But that sun and the sun really makes up about 98% of the mass of the entire solar system. But that's a lot of daggum gas. And all that stuff is weighing down on the center. Now, during the course of a star's life, it is constantly dealing with pressure from nuclear reactions in its center, wanting to blow the star apart, and the force of gravity wanting to bring it together. Wanting to keep it together. This fight goes on forever. This is the cutaway of the star. Inside the star, this is where the action is. This core is all we'll be talking about tonight. And the fate of that core depends on how much core is there and the size of the star. Basically, when you have a star, in that core is hydrogen gas, ideally. And there are nuclear reactions that occur in the core. And it requires, I think, 10 million degrees for these nuclear reactions to take place. What happens is the hydrogen combines to form helium, and it just happens in spots. There's another helium, a nucleus of helium being produced. There's another nucleus of helium being produced, and this goes on and on and on for, in our star's case, about 10 to 12 billion years to use up all of this hydrogen in its core. What happens is all of this helium gets produced until the helium itself carries on a self-gravity and it displaces the hydrogen in the center, and the hydrogen is then pushed out into a shell. Now the helium in the center of the star during our sun will then convert that later on in its life to carbon and oxygen and that type of thing, but that is as far as it goes. It cannot produce any more fuel from this because it just does not get hot enough to go any further. And what happens is the outer envelope, everything else out here, as the star swells later in its life, all of this, except for what's left of the core, all of this will quietly be blown away. This is the Ring Nebula. And this is what you would call a planetary nebula, from what previously used to be a very massive star. And what's left of the core of the star is now reclassified as the star, but it is the white dwarf material, a product of all of that compression. So it's about the size of the Earth, but it has the mass of the sun. Escape velocity is about 0.02 c. Now, here's a little equation that I did not cover in high school. What we were talking about before with all of those electrons and those protons hitting that critical mass of 1.4 solar masses, that electron is actually absorbed inside of the proton. So you can see here that once you absorb that proton into electron, it turns it into a neutron. So if you do have that, what you would have is, and once you compress that white dwarf into, the electron into the proton to become a neutron, there's something that occurs that I would like to call a change in volume. You would go from the size of something like this to where all of those electrons are absorbed to to the size of something like this. You go from the size of something of the Earth to the size of something of the island of Manhattan in half a second. Now, when we were talking about the surface of the table, not overcoming that, those neutrons, once you have that volume change from the size of the Earth to the island of Manhattan in half a second, it hits the surface of those neutrons. Those neutrons become basically its tabletop. That is a lot of velocity, and when you hit that tabletop, you end up with a very, very powerful explosion. And it looks something like this. Well, this is the temperature inside. There's a collapse and a very big explosion. This is an extremely bright explosion. And those other heavy elements are beyond carbon and hydrogen are produced as a result. And what is left behind is what you would call a neutron star. Now here's an interesting little tidbit I'm going to go over. Which is brighter? A supernova explosion, the distance of the Earth, or a hydrogen bomb? Now you have to have your eye open to conduct this experiment. Or a hydrogen bomb at the surface of your eye. Which would do more damage to your retina?
I think it's a moot point, but.
Huh?
You find my letter.
Believe it or not, the supernova explosion, the distance of the sun, would do more damage to your retina than having a hydrogen bomb up to the surface of your eye by an order magnitude of 9. The supernova explosion is extremely bright, extremely powerful. When it goes from the size of the Earth and hits the surface of all of those neutrons, that is one of the most spectacular explosions in the universe. But the remnant of that is a neutron star. It is 8 to 18 times the mass of the sun. And we've seen the mass of the sun previously. That compressed down to the size of Manhattan, the line on Manhattan. It's about 20 kilometers in diameter and has a density of 10 to the 14 grams per cc. 1 teaspoon is 1 billion tons. The escape speed is 70% the speed of light. We're almost there. Now, this is where another person of Mr. Robert Oppenheimer, who you guys may be familiar with because he was a lead physicist on the Manhattan Project. But prior to working on the Manhattan Project, he also, in 1939, published a paper on the continued gravitational contraction of matter. What he was trying to do was the same thing that Chandrasekhar did, to find out what's the limiting mass of the, Chandrasekhar did it with white dwarfs, he was trying to do it with neutron stars, and ended up finding out that the force of gravity beyond about 2 to 3 solar masses for a neutron star could not be stopped by any atomic or subatomic particle. It would just continue contracting. What I want to do is I want to take a look at the relative size of stars, because we want to take a look and see what could produce something like this. This is not very long. This is the size of the Earth. This is the size of our sun, okay? Next to our sun is a star called K9. I cannot remember the name of the star, but it's about 300 times the size of our sun. Next star in line is Betelgeuse. Betelgeuse is, I mean, this thing is enormous. This is the star that is about to go supernova in a moment. And this is the largest star ever on record. I forgot the name of the star too, sorry about that. But if our star, in its core, produces a white dwarf, what's going on in the size of, in the cores of these more massive stars? Where you would have helium displacing hydrogen, oxygen and carbon displacing helium and then hydrogen. Here you have a nestling of a lot of other elements because it gets so intensely hot in the center of these more massive stars. These things fuse all the way up to iron. But they don't go supernova. They don't have a chance to go supernova. While the star is still forming in the center of its, in the core, let's take a look at what actually goes on in the core of these stars. We would peer inside these stars. In its core, there's a lot more going on in our small star. There's all of these elements, all being fused and produced and displaced, all the way down to where at the central core there becomes iron. Iron is then compressed beyond or past electron degeneracy, beyond neutron degeneracy, and it starts to collapse in on itself. The central core does. That's what's going on in the inside, while this is going on the outside. On the outside, eventually the star collapses on in the inner core, and what happens is it explodes from both poles. And this occurs because of there are these magnetic fields that are generated at the poles of the star as a result of this thing compressing so fast, so small, there's a tremendous amount of spin. This is the old ice skater thing. You know, our sun has magnetic lines too, but it only produces these little arc things that just go down. It's really baby. You know, these stars, look at it, isn't that cute? These things produce these gigantic electron pulses, and they just distribute them above and below. The collapse of that core has formed what you would call a singularity. All of that matter, all of that tremendous amount of matter, where did it go? I mean, we've seen a lot of these massive stars, tremendous amount of mass compared to the Earth, and its, in its puny little gas. A lot of matter, enough matter to actually drive fusion, to produce elements of all our universe. Where did all that matter go? I'm sorry. As a result of all of this gravitational concentration, these things distribute a lot of X-rays, radiation. Oh, I'm sorry. I'll come a little later. Because of the star was destroyed from the inside out, this is what's left of the star, of the original star. There's a lot of, in most cases, there's a lot of trash, dust, particles, and all these types of things that actually come and try to engulf inside of the black hole. But all of it can't get in at the same time. It all comes down and it speeds up and gets compressed at what you would call the event horizon, or at the Schwarzschild radius. It heats up to tremendous amounts of temperature, and emanates a lot of radiation, most of this in the form of X-rays. But all of this is the emission of those X-rays are done at the surface of the event horizon, not from the black hole itself. But all of that matter, I'm sorry, we'll get to that in a moment. This is the first black hole that was discovered back in 1964. The heat from all of those dust particles and that type of thing, and this is produces the X-rays, and this is probably one of the most powerful X-ray producer that's been discovered, and it is a black hole candidate. Estimated to have a mass of 14.8 times the mass of the sun. The radius of the event horizon is about 44 kilometers. It's also in a binary system with a large blue supergiant. This blue supergiant is very massive, and the solar winds from this is constantly feeding this particular black hole, which is serving as a constant source of the emissions from the black hole. They estimate that the original star had a mass of 40 solar masses. Now, this is where we're going to ask the question, where did all that matter go? To answer that question, we have to look at one thing. This is one of Einstein's equations. We said that matter curves space, but if we look at the Einstein's equation, we have that matter is equal to energy. It's not that the matter curves the space, it is the energy that the matter possesses that curves space-time. Matter itself is just an expression of energy. But how much energy is in matter? There's a particular constant missing here. Is the energy in matter equivalent to, is it twice the amount of matter? Is it 10 times the amount of matter? Or 100 times the amount of matter? Is it 300 million times the amount of matter? Actually, no. It is actually 300 million squared the amount of matter. That's how much energy is in matter itself. So you can, from a very small amount of matter, you can get a very tremendous amount of energy. We've kind of exploited this, and knowing this, we've kind of exploited by taking these unstable atoms and trying to use those as bombs, but we're really kind of cheating a little bit when you think about it, because these things, they're not stable anyway when you knock those apart. And anyway, all of that energy has been converted into the curvature of space-time. That's where that energy went. There's no surface to the black hole. Those molecules have been destroyed. There's no subatomic matter that we know of in there. Those things have all been destroyed. Even at the black hole, there aren't two atoms that go together, because those things have been compressed by the tremendous amount of gravity that has totally destroyed all matter that we know that we know of, that mankind has been studying since the beginning of time. All Aristotle, Plato, these guys, it's gone. It's gone bye-bye. What lies beyond, now we've discussed the mechanics of building a black hole, but what are the effects of a black hole? Let's try, for example, falling into a black hole. before we talk about falling into a black hole, let's look at one thing. Relative motion. This looked more scary on the slide than it did in doing it. This is on our car. We're in a car. My daughter's taking this. I'm driving.
As long as I stayed in jail, I'd be safe.
But as you can see, how fast is this car going? We may be going about 60 miles an hour. But for this van, it looks like it's traveling about 30 miles an hour. As a matter of fact, as I pass this car, we take over, and if we look at it, it looks like the car's not moving at all.
You know you're a lucky guy.
To someone on the road, these cars are whizzing by.
You know you can get distracted.
But from our point of view, from our frame of reference, this car is stationary. Ignore the background. I can literally leave my car and walk into the other car. And as you approach, the point of this is, and this is something that, like I said, these things are all around you. There is no such thing as absolute motion. All motion is relative. From the ground, these cars are going 60 miles an hour. But from your frame of reference, these cars can be going, 10 miles an hour, or not moving at all. Let's discuss gravitational redshift. This is where, according to Einstein's second postulate, when we talked about it being blue at the surface, but expending its energy at the expense of its frequency, trying to escape this gravitational field, it's more red because the frequency has gotten longer. But the speed of light is the same. How is that possible? It is because the time here is slower than the time here. That's how we can have a longer wavelength of light here, but still measure the same velocity of light. That's the importance of the second postulate. It's a direct result of the gravitational time dilation. Now here we would have, if we were to fall into a black hole, I'm going to have this. Jeremy, can you hold this one? No.
Careful, it's a black hole.
Yeah. Yeah, it's a black hole. It's orange, but it's supposed to be black. Yeah. Let's say we have two space travelers. This is our black hole. Immense amount of gravity. There is a lot of warpage of space-time here. As a result, time itself is slowed to the extent of that. We have two space travelers. One kicks the other space traveler out. What does he see? The space traveler goes tumbling towards the black hole. This traveler sees him accelerating, as he normally would, just like he would accelerate towards the Earth, accelerating towards the black hole, accelerating. But as he tumbles, what he would also see is because of the redshift, because of that Doppler shift, because of that time dilation, he would also see his tumbling slow down. He would see it slow as he approaches the black hole. He's not tumbling as fast. Also, he would see the color of his suit change. It would become more towards the red part of the spectrum, up until he gets to the event horizon, where he will see him freeze. He will see him not stop moving. As far as he's concerned, this is where the frame of reference and relative motion and that type of thing. As far as he's concerned, this guy is frozen in time right here because of the immense amount of gravitational curvature here. That's what he observes. And he will see him sit there and freeze forever. He may change his mind and wonder why. He may say, I see him there, I'm going to go get him and rescue him from there. But he doesn't know. His friend is long gone. But that's what he sees. What does he see? He passes through. He doesn't see a daggum thing. His clock is running the same. He's still tumbling at the same speed. He passes through the event horizon from his perspective. As I just passed, I come close to Jeremy. He doesn't even recognize. It's almost like crossing the state line into Arkansas. He doesn't recognize anything. He just knows that there are a lot of mosquitoes and people with no teeth all of a sudden. So once he gets in, there's a tremendous amount of what you would call tidal shift. Thank you. One other thing. Not only that, but he would actually see him because our eyes are only sensitive to that small sliver. As the light fixtures from, he will actually see his friend disappear because of human eyes. They can't see radio waves or anything, so he would actually see his friend disappear because of that redshift. And the tidal forces, spaghettification. We all know that the force of gravity is proportional or inversely proportional to distance. Okay. Distance? Square of the distance? Yes. And but inside the black holes, stellar mass black holes, that distance is extremely sensitive to where not only you know something from the surface of Earth to the moon, but even my height, even the head, from the distance from my head to my feet. So the force of gravity on my feet would be a lot more than my head. The unequal, it would pull it in on the sides, and you end up being stretched in half, and then the force, and then all of a sudden you're a string of atoms going towards the singularity, whatever that is. Okay, now this is our last thing we're going to discuss. I'm gonna free you from the night. This object, I take it. I work against the force of gravity to lift it. We're not going to go through all the math, but just the idea. We go against the force of gravity to lift it up to a certain height. I expend a certain amount of energy in doing that, in lifting this to a certain height. Once I achieve this height, where did the energy go? Where did the energy go? The energy is stored in the height of this particular object. That's the gravitational potential energy. It's distance from that type of gravitational potential energy is we've exploited that in waterfalls to do work or in various ways. But that is particular to the surface. It's not particular to the surface of the Earth. When you let go, that gravitational potential energy turns into kinetic energy. When it hits the surface, that kinetic energy is released in the form of in sound. It's absorbed within an object. If that object can absorb that, it will not break. If it's more energy than that particular object can absorb, it will shatter. This is dropping something on the surface of the Earth. That is an example of the energy that is a result of that. There is so much gravitational potential energy on the surface of a neutron star that if I were to take something as light as a marshmallow, and drop it on the surface of a neutron star, it would release the amount of energy equivalent to tremendous amount of energy because of the density of this thing. So imagine if I took a black hole and dropped it on another black hole. What would that look like?
Gravitational waves.
Huh? Well, the mechanics of that impact is a little different than just a vertical drop. What you would actually get are two black holes inspiraling, and this comes from a binary system, inspiraling with each other, and they would impact. And if something as light as a marshmallow can emit that much energy on a neutron star, this is the most cataclysmic collision in our universe. The collision of two, or the impact of two black holes. It emits a lot, and the result of that, it isn't an explosion like with a sewer. It isn't a radiant energy and that type of thing. Nothing faster than the speed of light can, less than the speed of light can escape these collisions. It's quiet. It's a quiet explosion, but it is the most powerful one in our universe. But what does happen is that it emanates a tremendous amount of gravitational energy. It's like taking a curved space-time and thumping it. Well, how do we detect this sort of thing? What we have is the LIGO. It's the Laser Interferometer Gravitational Wave Observatory. And because of the distance of these collisions or merging of black holes, these things have to be able to detect an effect of gravitational wave energy 1,000th the diameter of a proton. It's pretty small. How do you do that? These observatories are set up in, right now, I think, in 4 areas of the world, or 5 areas of the world. There are 2 in North America, in Washington and Louisiana, I believe, and in Europe, and they're going to be building a 5th one or a 6th one in India. I don't know when that will be ready. But these observatories all look something like this. When that gravitational wave comes through space and hits the Earth, there is a compression in this way and tension in this way. So what you do is you set up these long arms, these long observatory arms here, to detect, and you fire laser beams. Have a laser go out, a beam splitter. You send one about 4 kilometers or 2.5 miles away in one direction, and 2.5 miles away and at 90 degrees to that. What's going to happen is they will reflect off of mirrors, they will recombine here, and what you do is you look at the interference pattern. These are very high precision pure light lasers, and I don't have to tell you all of that. I mean, these are very high precision glass. And the precision comes from the length of the things. If there is a difference in the time, in the return times of these return reflected light beams, 1,000th of the diameter of a proton, this thing will find it. But it has to be confirmed by several of the other observatories. What it would look like as a result of those, this is going to be an exaggerated version of a gravitational wave coming through the Earth. Now, when this happens, you cannot carry trays of liquids and that type of thing. So don't carry your fine china while this is going on. But those things can detect those differences by the interference patterns. And I think they detected about 3 or 4 instances or episodes so far, and they are very excited. That's it.
Any questions?